In Lecture 11, we're going to talk about oxidation and reduction reactions. This lecture is going to be short and sweet, and we're going to have to approach this slightly differently than we have in the past. We're going to do quite a few examples just to get the concepts through. Again, we'll have to start with fundamentals, and for the fundamentals of this lecture, we're going to go into some definitions. An oxidation is simply stated as the loss of electrons, and the reduction being the gain of said electrons. An oxidizing agent is one that oxidizes another compound, and a reducing agent is one that reduces another compound. Make sure you know how to assign oxidation numbers. Some general trends are going to be covered later on in this lecture. There are different ways to remember oxidation. Two in particular. There's oil rig, which is noted as oxidation is loss, reduction is gain, and there's also Leo says Ger. I prefer this one because it actually says what you're losing or gaining. It simply states losing electrons oxidize, gaining electrons reduce. However you choose to remember oxidation and reduction is completely up to you, but these are two ways you can remember them. What is a half reaction? A half reaction is taking a reaction, an oxidation reduction reaction, and splitting it in half into two split reactions, the oxidation step and the reduction step. The steps are listed below. Let's go through an example. How about if we were to do this one? So MnO4 plus MnO4 minus plus I minus. How about we do that one? So MnO4 minus plus I minus, and this is going to get us I2 plus Mn2 plus. Now, obviously this isn't particularly balanced, and the oxygen just dissipates off. Also, it isn't balanced just yet, so we're going to have to continue. This is clearly not finished, but to balance this, let's look at the two steps. So we have I minus going to I2, and we also have MnO4 minus going to Mn2 plus. So, if we look, let's balance this through. So the iodine, if we were to balance this out, we would have to put a 2 in front and run this across, getting us I2 plus 2 electrons. This is obviously losing electrons, therefore that's the oxidation step. This one, on the other hand, MnO4 minus, is not quite balanced, so we're going to have to do something to it. In this case, we're going to add 8 protons and run it across to make Mn2 plus and 4 waters, 4H2O. There, now we've got it all balanced out. Once we consolidate the two, we have to also take into account what's going on here. For starters, it's not balanced through because we have a disparate number of electrons. We're going to have 8 hydrogens and 5 electrons to offset the charge. Now obviously we can't quite run this just yet, so we're going to have to take both and make them common, meaning that we need to have an equal number of electrons going across. Now 2 electrons here and 5 electrons here. So simply we have to multiply this all across by 5 and this all across by 2, netting us 10I minus to 10I2 plus, or 5I2, excuse me, 5I2 plus 10E negative. And when we run it across on the other one, we would get 10E minus plus 2MnO4 minus plus 16H plus goes to make 2Mn2 plus and 8H2O. What do you notice now? Well, we can cancel some things out, starting first with electrons. Those are all finished out, so now we can write the entire thing. 2MnO4 minus plus 16H plus 10I minus goes to make 2Mn2 plus 5I2 and 8H2O. So here we go. There is our completely balanced reaction using half reactions. As you can guess, if I were not to do this, it could take me a very long time to balance this, but using oxidation and reduction steps, we can find a much easier way to balance. The simple way to balance this is just to take note of how many electrons are running around, and that they have to cancel. Also, if there's oxygen present, generally speaking, you're going to have water on the other side and protons on the side with the oxygen, so as to make sure that everything is accounted for. That'll bring us into net ionic equations, and there's two types. There's the complete ionic equation, which is when all ions are present, and net ionic equations when the spectator ions are ignored. A disproportionation reaction is noted as a species that is both oxidized and reduced. You will generally not see these on the MCAT, so we're not going to worry about these too much. What we can do at this moment, though, is actually go into some net ionic reactions. So let's go into an example of it. Let's use the formation of hydrofluoric acid. So we have H2, and this is gaseous, plus F2, also gaseous, making HF. Now for the purpose of simplicity, we're going to call this aqueous. These are pure and standalone, so their oxidation states are going to be 0, whereas this one is going to be slightly different. So let's break this out into half reactions. So for starters, we have H2 going to H plus, and this obviously isn't balanced, so we have to take two of these. Now there's two positive charges, therefore there has to be two negative charges to account for this. The other side would be noted as this. So this becomes negative, therefore there has to be two electrons on this side in order to get 2F minus. Now, what you'll notice is, based on this has to be balanced. Therefore, there has to be a 2 right there. So, after we finish this is already ready to go, so we can cancel these and get us set. So, the net ionic equation is going to be noted as H2 plus F2 goes to make 2H plus 2F minus. So that would be the net ionic equation. If you remember from our second lecture in the series, we went over periodic trends. Another area where those are going to come in very handy is when we're talking about oxidation states. Alkali metals are always going to have a +1 oxidation state. Alkali earths +2, and the trend continues. There's those two on one side, and then you've got the halogens and the chalcogens on the other. But the trends are noted as such. One thing you're going to note is that the transition metals don't have defined oxidation states because they fluctuate. You could have iron 2+, iron 3+, all the way up to iron 4+ possibly. So in general, they don't follow very many trends. The trends that are family dependent, though, are listed, and it's really in your best interest to have these memorized. So I know the lecture was very short and sweet this time, but this subject is important nonetheless, especially when it comes to balancing equations. Make sure you have a good handle on oxidation and reduction reactions, and make sure you don't get those definitions confused. In the next lecture, we're going to go into electrochemistry to round out the general chemistry module.